Hello, in this video we're going to talk about manipulation of power series. So basically new from old. How can we use existing power series to get some new power series or power series from related functions? So first of all, we can apply some algebraic techniques and then also some calculus manipulations to certain existing power series to obtain a power series for a new function. We're going to look at several of these techniques in this section. The first thing, let's talk about some calculus things we can do. Well, one of the most basic things we can do is find a derivative. So derivatives of polynomial functions, remember, are very easy to find. We just use the sum rule and the power rule and maybe the constant multiple rule, but we could do those in our heads very easily. The same standard rules for finding derivatives of polynomial functions can be applied to finding derivatives for power series. We apply an infinite version of the sum rule for derivatives and then apply the power rule to each term. So it works out like this. We have the derivative of the sum is the sum of the derivatives. It's basically the sum rule. And the constant multiple rule can be pulled out front. And then the power rule is applied here. It's u to the k. So it's k times u to the k minus 1 times the derivative of the u. The derivative of x minus a is just 1. So it's just basically take the derivative of each term infinitely many times, and this still works for a power series. So the center and radius of convergence for the resulting derivative series is the same as for the original series. However, the behavior at the endpoints of the interval sometimes changes, so we have to recheck the endpoints to see if the series converges or diverges there. So, for example, let's use derivatives to find the Maclaurin series expansion for cosine of x, given that we know the expansion for sine of x. So recall that the sine of x, the expansion, is the sum from k equals 0 to infinity of negative 1 to the k over 2k plus 1 factorial times x to the 2k plus 1. Remember, what we get is the odd powers of x, and then it's 1 over that power factorial, and then we have an alternating sign, plus, minus, plus, minus, plus, minus, and so forth. Okay, so you can kind of see some terms written out here. And this is true for x's that are any real number. So the cosine we can get is the derivative of sine. So instead of working out cosine directly from Taylor's theorem, which we've actually already done earlier, we could do it instead by doing the derivative of this term by term. So let me just look at the term by term level, and then we'll look at it with the summations. So the derivative of the first one is just 1. Then here we get 3 times this. Well, that 3 is going to cancel the 3 out of the 3 factorial, leaving only a 2 factorial, and then we're going to have an x squared. So we have 1 minus 1 over 2 factorial x squared. And then we multiply by the 5, it's going to cancel that 5 out and leave a 4 factorial, and we're going to have x to the 4th. And then we do the derivative of this one. The 7 is going to cancel out the 7 out of the 7 factorial, leaving a 6 factorial. And we have x to the 6th, and so forth. So written out with summation notation, the derivative of cosine x is the derivative of sine x. So sine x can be written as this sum. And so the derivative of the sum is the sum of the derivatives. And then what we do is we take the 2k plus 1 times this, cancels the 2k plus 1 out of the factorial, leaving 2k factorial. The negative 1 of the k is still there. And the power goes down 1. 2k plus 1 minus 1 is just 2k. And so we get that. And that's exactly, of course, what we got when we used Taylor's theorem directly to find the series for cosine of x. Perhaps this would have been easier working out this way, given that we already had the derivative for sine x, or had the series for sine x, we could find the derivative. So we can show that the derivative of e to the x is e to the x if we started with this power series. Of course, we used the fact that the derivative of e to the x was e to the x to obtain the series, and we used it to prove the general power rule. So, I mean, we've actually been using this way back all along, but if one took the e to the x equals x to the n over n factorial sum from n equals 0 to infinity as the definition of e to the x, which some folks do, then we could prove the derivative of e to the x is e to the x by the following method. So the derivative of e to the x is the derivative of that sum, which is the sum of those derivatives. And we multiply the n times this. Well, the n in the numerator cancels that n in the denominator, leaving n minus 1 factorial, that should say. Yeah, it's still n factorial because I got the n at the top. Now cancel, leaves the n minus 1 factorial. Well, we have notice that when you do this, the sum actually now starts at 1 to infinity because that 0th term, the derivative was just 0. So that term just goes away. So really we're only left with terms 1 to infinity, not a 0th term here. Okay, well, now what do we get? We get x to a power, all the powers there, n minus 1, and the same n minus 1 factorial in the denominator. Well, if I do a change of index variable, let k be n minus 1, then this n minus 1 becomes k. That power of n minus 1 becomes k. The n, when n is 1, k is 0. And of course, as n goes to infinity, so does k. And so this becomes the sum from k equals 0 to infinity of x to the k over k factorial, which is, sure enough, e to the x. Okay. In a similar manner, we can do integrals, okay, or antiderivatives. The antiderivative sum is the sum of the antiderivatives, and we use the basic power rule, add 1 to the power, k plus 1, and then divide by that k plus 1. I guess technically we should have a plus c, which I'll put at the beginning. We'll have a constant term show up as well, because notice now this is going to start out with a first power term, but there is a constant term there, to get the entire family of antiderivatives. In fact, instead of that plus c, I'm going to go ahead and write that as c sub 0, but it is our plus c from our integration. Okay. And the center and radius for convergence for the resulting integral series is the same as for the original series, but once again, you have to check the endpoints to see if it converges there. So, use integration to find the Maclaurin series for cosh, given that sinh is this. So sinh is x plus x cubed over 3 factorial plus x to the 5th over 5 factorial and so forth. It's the sum from n equals 0 to infinity of x to the 2n plus 1 over 2n plus 1 factorial. And we're going to use the initial condition that cosh of 0 equals 1 to solve for that c sub 0 to find the specific antiderivative. Okay, and I actually should put in the c sub 0 here. Let me get this fixed for you real fast. Okay, so here I've got it fixed up, I think. So we integrate sinh. Well, sinh is given by this series up here. Now, the integral of the sum is the sum of the integrals, or the antiderivative of the sum is the sum of the antiderivatives. And so we use the normal rule, add 1 to the power, that's 2n plus 2. Divide by the new power, so divide by 2n plus 2. Well, 2n plus 2 times 2n plus 1 factorial is 2n plus 2 factorial. And this sum is going to still go from 0 to infinity, but we pick up another term, a constant term here, which is arbitrary at this point. But we'll have to figure out what it is based on this initial condition up here. Okay, let's work on this part right here just a little bit. Well, notice this is x to a power by that power divided by that power factorial. And if you look, this is x starts at 2 and goes up. So another way, if we switch this to be k to be n minus 1, we can put that there. And this starts at k equals 1 to infinity, this is 2k factorial, and this is 2k here. So notice what happens. If k is 1, this is 2. K is 2, this becomes 4 for the power. K equals 3, this becomes 6. This also starts with powers of 2, 4, 6. Okay, and then this is C0. We use the fact that cosh of 0 equals 1 to plug in cosh of 0, plug in 0 on this, and all this sum comes away. So C0 is 1. And so it turns out if we allow 0 to the 0 to be 1 here, then for any x that we put in, k equals 0, this is a power of 1, a power of 0, which becomes 1. And this is 0 factorial, that's also 1. So this works out the same if we just say it's the sum from k equals 0 to infinity of x to the 2k over 2k factorial. And that works out. So that's using derivatives and integrals of power series to get new power series. We'll look at some other techniques in the next video.